Welcome dear students. Now next video is regarding detection of ultrasonic sound, and there are four important methods to detect ultrasonic sound. Now ultrasonic sound gets propagated by compressions and rarefactions. I will show you a diagram. Here you can see this diagram. See, here you have compressions. Here you have compressions. Here you have compressions. At this point of compressions, we know that the particles will come closer. So that point will have more pressure. We will have more pressure at compressions. And these regions, the one with white in color, these regions are regions of rarefactions. There the molecules are away from each other, so their pressure is very less. So that idea we will be using in this. So at compressions, when you keep a piezoelectric crystal, that crystal will experience more pressure, and you can see that according to piezoelectric effect, it will have charges developed across electrical axis. Now this can be used to detect piezoelectric method effect can be used to detect compressions of the ultrasonic wave. So once you get standing waves, you can find out the compressions and rarefactions of the ultrasonic sound wave using quartz crystal method. Main idea of working of this quartz crystal method is piezoelectric effect. So you can find out the areas of compressions and rarefactions, and the potential difference developed can be amplified by an amplifier used to detect ultrasonic sound wave. So that is first method. Now again, compressions and rarefactions are used to detect ultrasonic sound in a different way. That method is called as thermal detection method. So thermally you can detect. The idea of compressions and rarefaction is used in a different mode. At compressions, I already told you, the particles will come closer and more particles are seen in small distance. So since there will be more collision of particles, temperature will be high at compressions, and there will be less temperature at rarefactions. So that is where the rarefaction is. You can see that at rarefactions, molecules are away from each other and there will be less collision. So temperature will be very less at rarefactions. So since temperature is very less, you can find out rarefaction easily and compressions can be detected easily. Now using this, here we will be employing a platinum resistance thermometer. Platinum resistance thermometer is used, whereby the resistance of the platinum wire is changed with respect to temperature. I hope you remember the formula R equal to R0 into 1 plus alpha T, the temperature dependence of resistance. So resistance dependence of temperature dependence of resistance of any metal, that is given by this formula. So as the temperature changes, resistance of the wire changes, and you can detect the positions of compressions and rarefactions. So that is how this thermal detection method works. Now there are two more methods. Let me explain you. They are very simple. First one is sensitive. The third method is sensitive flame method. So again, we know that compressions and at rarefactions, pressure will be different. At rarefaction, when you keep a flame will not flicker. At compression, when you keep a flame will flicker mainly because pressure is high. So you can find out the position of nodes and antinodes easily with respect to flickering of flame. When the flame flicker frequently, you can find out that is compression. When the flame is not flickering, it is rarefaction. So now with using that, you can find out the wavelength of the ultrasonic sound wave. The fourth method, that is not that important, but anyway, for mentioning, that method is called as Kunst tube method, where powder is used to some powder, that is lycopodium powder, is used to find out the wavelength of the material. So for this, a tube is taken, and here you have a piston. Powder is sprayed over here. Then here you have an ultrasonic transducer. This ultrasonic transducer will produce ultrasonic sound. So that is how this works. Now, after producing, once the transducer starts producing ultrasonic sound, piston is adjusted so that standing waves are formed in the tube. Now, after some time, you can see that the lycopodium powder will get arranged in the form of heaps of regular interval. From this, you can find out the nodes and antinodes of lycopodium of the waves. At nodal points, so movable piston is adjusted to produce standing waves. Now the powder collects in heap at nodal points and blown off at antinodal points. With that, you can find out wavelength of the ultrasonic sound wave, and wavelength of ultrasonic sound wave equal to 2d. Here d is the distance between two adjacent nodes, and that is how lambda is found out, and velocity can be calculated as v equal to lambda of ultrasonic into f, where f is frequency of ultrasonic sound wave. So that is how we detect the ultrasonic sound wave. And the last method, that is called as Kunst tube method. Now we have application of ultrasonic sound waves. There are three main applications of ultrasonic sound wave. First is NDT, which is non-destructive testing. Testing without damaging the object, that is called as non-destructive testing. So normally, if you want to test the strength of a specimen material, for example, you have a tile making company and you want to test the strength of a tile, you have to apply some pressure on it. After some time, the tile will break. So that is destructive testing. Now here the tests are non-destructive testing, whereby you use ultrasonic sound wave to test the strength of the material. And there are three methods. First is pulse ecosystem. Concept is very simple. You will be using echo of the pulse, and then you will study the strength of the material. You can see that first the pulse is sent like this, and the pulse is received like this. So pulse sent and pulse received, they are of same amplitude and same frequency, everything. Now that is checked, their size and shape are same, so there is no problem in the material. Now again the pulse is sent from other side and it is tested. There is an additional part coming in the diagram, in the CRT diagram, that is flaw echo. That is due to defect in the material. So defect can be identified. Defect will appear in the CRT cathode ray tube as an additional frequency or an additional echo. So that is how defect is identified. So here different materials in this diagram, the specimen to be tested, then this is specimen to be tested, this is transducer. Transducer will produce the sound and it will receive the echo, and then it will display it on cathode ray tube. That is how this works. Second is pulse transmission system. Here we use two transducer on two ends of the material. Previously it was echo method. Now this is transmission methods. You see, there is one transducer on one end and another transducer which act as receiver. One act as transmitter, other act as receiver. So one produces the ultrasonic sound while the other receives the ultrasonic sound. Again the output is fed to cathode ray tube and that gives the final result. Now you can see that in the first diagram there is no defect, or the transmitting pulse and receiving pulse are same size, shape and or of same frequency. Now second diagram you can see that the amplitude of the pulse received has changed, which indicates that there is a problem in the material tested. Third is pulse resonance system, whereby resonance method of resonance is employed to test the strength of the material or test the consistency in the material. Now here when you transfer ultrasonic sound to the material, standing wave is set up and specimen vibrate or resonate with greater amplitude. Now resonant frequency is studied. If there is any discontinuity in resonant frequency, or if there is any change in resonant frequency, there is discontinuity in the material. If there is any change in resonant frequency, there is discontinuity in material. That is how this is studied. So this method is called as pulse resonance system. Okay, these are three different methods of testing of ultrasonic sound wave. Let me stop here. We will come back with next video, next class. Thank you.